Lesson 4. Lesson 4 says series and parallel circuits. What we're going to do is we're going to break down the circuits into two main types. We're going to say that resistors are either in series or in parallel. We're going to define it. And then what we're going to do is see if we can tweak Kerkhoff's laws, Mitsu, so that they work for that. A series circuit is a circuit where the resistors are connected in a row with no junctions in between them. Example 1 says, which circuits show resistors in a simple series? Well, what you're really asking, Zay, is which circuit does not have any junctions? These resistors are all in series. Here, not in series. Okay. What that really means, Connor, is if I wanted to give you a definition involving circuit and current, two resistors are in series if the same current goes through both of them, if the same skiers go through both of them. We all got to go through these three are all in series. And what I'd like to do is try and come up with a mathematical expression for the total resistance in a series circuit. You see, Kara, what we're going to be doing today is analyzing circuits that are a little bit tougher. One of our methods, along with Kerkhoff's laws, is going to try to be to mathematically rewrite the circuit as one resistance, one current, and one voltage. And then we can use V equals I times R and kind of backtrack our way, figuring out what needs to be what. Okay. Says find an expression for the total resistance. Well, Kerkhoff's voltage law says this: the total voltage equals the voltage in resistance 1 plus the voltage in resistance 2 plus the voltage in resistance 3. Once you've written that down, put your pencils down for a second. In other words, Joel, here's what we're saying. Don't write this down. If this battery is 30 volts high, how many volts must I lose going through all three of those resistors grand total? Got to, so I can get back to the bottom. It might be 25 and 5. It might be 19, 3, and 8. I don't know what the voltages are in each resistor, but I know one thing. They add to 30. Is that all right? Oh, not only that, Kerkhoff's current law says, how does the current in here compare to the current in here, compare to the current in here, compare to the total current? Arvinder, the same. See, this is nice. It's called success. Good feeling. Yeah, look, all the skiers that leave here go through here, go through here, go through here. Total current is equal to the current in the first one, not plus, Mr. Dueck, is equal to the current in the second one, is equal to the current in the third one. Now, what about total resistance? Well, Sean, we know this. Also, although I've never specifically said this, total voltage is total current times total resistance. Sean, can you get the R by itself for me? Turns out it's going to be total voltage divided by total current. Mitchell, what's total voltage? This. All over. What's total current? That. Now I can rewrite this as V1 over I total plus V2 over I total plus V3 over I total. I can break up a fraction if I can break up the numerator of a fraction. I can't break up the denominator of a fraction. This is also true. And we're still trying to get an expression for the total resistance. Well, what is V over I based on Ohm's law? What's V over I based on Ohm's law? Look up. It's right here. Just rearrange it. What's V over I based on Ohm's law? Matt. So, what's V1 over... Oh, is I total the same as I1? V1 over I1. You know what? That's resistance 1. And you know what V2 over I total, which is also I2 is, Andrew? That's resistance 2. You know what V total over... You know what? That's resistance 3. Here's the rule. Brett, if resistors are in series, you can just add them up. Do we have that in the box? Yes, we do. The total resistance is R1 plus R2 plus R3 plus R4. If they're in series, you can just add them up. If I stick a 3 ohm resistor right next to a 4 ohm resistor, mathematically, Caleb, that's the same as 1 7 ohm resistor when they are in series. How's that help? Ooh, helps lots. You see, I told you the other day that usually if they give me a circuit, I'm really trying to find, before I find anything else, the total current, because once I have the total current, it falls apart. Have they mentioned current in here anywhere? Okay. Brett, are these two resistors in series? Then you know what? Can you tell me the total resistance of this circuit, the mathematical equivalent? 25. Oh, and do you know the total voltage, the chairlift? I total equals V total over R total. There's V equals I times R, but Mitsu, I've rewritten Ohm's law. What's the total current flowing through this circuit, leaving the chairlift, leaving the battery? In your head. Arvinder. Oh, that's the answer, Mr. Dueck. Right to 25 there. So, right there we have 4 amps. Arvinder, how many amps right here? Oh, do I know 2? Then I can tell you the voltage drop right here as well. How many volts do we lose going across this resistor? V equals what times what? Oh, 20 volts? How high were we when we started? How many did we lose here? How many volts must we lose here? And the other way you could have got it is you could have realized, hey, the current is 4 amps, and you could have gone I times R. In fact, I can get it now 2 ways and get the same answer both. I'm pretty sure I'm right. And I can answer the question. It says, select the best answer for the voltage drop across the 20 ohm resistor. 100 volts, more than 50, less than 50. The voltage drop across the 20 ohm resistor is more than 50. Explain your work there. I just did. I solved it. It's not just more than 50, it's exactly 80. We can use this idea of series resistors, add them up, find the mathematical equivalent, to then go, well, if I can find the total resistance, total current is total voltage divided by total resistance. And almost always, Mitchell, I'll know the total voltage, because almost always I'll know the battery. Example 4 says, find total resistance and current, and then find the current through and the voltage drop across each resistor. Okay. Nicole, these 3 resistors, are they in series? Oh, so can you tell me what's R total? What's V total? I couldn't hear you, sorry? When I say I couldn't hear you and you say it the same volume, it doesn't help me at all. 100, yes. Oh. Total current. Right, I'm using V equals I times R. I told you this is the equation we're going to be flogging to death, and you'll end up memorizing it. Katie, V equals I times R, get the I by itself, yes? Katie, what's the total current running through this particular circuit? By the way, if I asked you that, make sure 4.0 if it was a final answer, 2 sig figs, right? So, what's the current right there, Katie? Look up. What's the current right here? Ah, what's the current right here? Yes, that's Kerkhoff's loss. What's the current right here? Yeah. What's the current right here? Yeah. Oh, do I know 2? Then I know 3. Actually, I could find the power if I was bored as well. What's the voltage drop across this first one? 60 volts, 20 volts, 20 volts. Double check. Hey, that adds to 100. Oh, heck. What's the power in this resistor? What's the power in this resistor? What's the... If these were light bulbs, what's the brightest bulb? Let's see. Power, so we have V equals I times R, and we have power equals what? Brett? It's on your sheet. Be active learners here. Okay. V times I, oh, this is 240 watts. V times I, this is 80 watts. 80 watts. Oh, that top bulb is the brightest bulb too. Leave Brett alone, Matt. She's trying to learn. All right. That's series. The other type of circuit is a parallel circuit. If you've done any electronics, you've heard both of these terms before. A parallel circuit is a circuit where resistors are, cross out the word are, where resistors start and end at the same height, voltage. I.e., the resistors are directly connected at the top and at the bottom with no other resistors in between. Which of these shows resistors in simple parallel? Well, can we shake hands? One group go this way, one group go this way, one group go this way. Each of us ski down one hill and end up back at the same height meeting over here. If we use our skier analogy, this is simple parallel. This one is not simple parallel because these two here are in series. Now, if I needed to, Brett, I could, if I was trying to solve this, I would combine these as one resistor by just adding them together. That's the series rule. And then I would say I have something similar to this, but without that there. What we want to do is find an expression for the total resistance of a parallel circuit. Unfortunately, this is the tricky one. First of all, don't write this down, just watch. If this is 80 volts, how many volts do you lose going through here? 80. How many through here? 80. How many through here? So what I do want you to write down is, I think V total equals V1 equals V2 equals V3, yes? If I call this current 1, current 2, and current 3, the current law says this. Total current must be I1 plus I2 plus I3, because we do all meet right here coming back together. Right, Nicole? Then it says total resistance, and for reasons that will become clear in a second, I'm actually going to find the reciprocal of resistance. So if V equals I times R, Sean, what was an expression for R? What's an expression for the reciprocal? I over... No, too complicated. What did you tell me an expression for R was? What's an expression for the reciprocal of R? I over... Yeah, that's it. Okay? Total resistance is... Change colors, Mr. Dueck. Total current over total voltage. Mitchell, from the previous line, what's my expression for total current? Is that okay so far? I'm going to break this fraction up again. I'm going to rewrite 1 over R total as I1 over VT plus I2 plus V2, Mr. Dueck. Let's try that again. Why I'm slanting down, I don't know, but apparently I am. Less laughing, more learning. Is that okay, Katie? By the way, what can you tell me about the total voltage compared to voltage 1, Katie? And compared to voltage 2? Compared to voltage 3? So you know what? I'm going to say voltage 1, voltage 2, voltage 3. Sean, you answered this a few minutes ago. What's I over V? What's I over V? I think it's not R. What is it? 1 over R. So what I've just found that is expression for 1 over R total is 1 over R1 plus 1 over R2 plus 1 over R3. This is the expression for parallel resistance. If you're finding the total resistance in parallel, you actually find their reciprocals, and then when you're done, take the reciprocal of your answer. It looks like this. 1 all over Say what? Let's look at, it's easier to do with an example. And you want your calculators out. Because this is where we generally, because you guys suck at fractions, reach the point where we can't do math in our heads. Having said that, I'm not going to bother. I'm going to go to decimals and let my calculator do this completely for me. Jacob, what does example 7 want me to find? And I, for everything. In other words, you know what it's really saying? Find everything on everything. This, we already know the voltage, we don't care, but we're going to find the total current. And then we're going to find three things. Heck, we're going to find 4. We'll stick power on there too, just for the heck of it. I'm curious which of these bulbs is brighter. The bigger resistance or the smaller resistance bulb, I wonder. Okay? Do I know the total current anywhere? Then that's what I want to find Brett first. Because if I find that, it falls apart. How am I going to do that? First, I'm going to find the total resistance. 1 over the total resistance is going to be 1 over 10 plus 1 over 15 plus 1 over 20. This is parallel resistor rules. Joel, you'll have to recognize that we are in parallel, but do you see the difference between parallel resistors and series from the previous example? Okay. I'm not going to get fancy here. I'm going to go to my calculator and just go 1 over 10 plus 1 over 20 plus 1 over, oh, I forgot the 1 over 15, 1 over 15. I don't know why I did it in that order, Kayla. I could have gone in the order that I wrote it, but it doesn't matter as long as I get all three. Hit enter. That is not the resistance. That's 1 over the resistance. Now, all of you somewhere on your scientific or graphing calculator have a button that maybe you've never used before. There is actually a reciprocal button. This one. The little x to the negative 1. And if you ever wondered why they bothered putting that on a scientific calculator, it's because of solving resistance circuits. You use it so often, it's handy. Take the reciprocal of your answer. That's the total resistance. The total resist, and by the way, this is where the numbers almost always stop working out nice, because I'm doing fractions inside of fractions inside of fractions, and then, forget it. I'm not going to try and make them work out nice. This circuit has a total resistance of, Joel, hello, look up, right there. Okay, that's your reciprocal button. And I'm going to carry a few extra sig figs. I'm going to go 4.6154. ohms. Now, this is not going to appear on my actual diagram. What I'm saying is, Arvinder, if I made a brand new circuit with a 60-volt battery and I wanted to replace these three with one resistor, you know how big that resistor would be? That big. Oh, do I know R total? Say yes. Do I know V total? Say yes. What? Rhett, what did I say I was really trying to find? Which one? There's 5 different ones in here. I didn't just say current. I said total current. That's the key. That's the key. We want to find what's leaving the chairlift. Well, I total equals V total over R total. It's going to be 60 divided by 4.6154. Although, since I have this number stored on my calculator, I'm going to go 60 divided by and use my answer button. Oh, this did work out evenly. You know what the total current in this circuit is? How many amps? Okay. Ready? How many volts? How many volts? Think about it. Ah! Oh, and how many volts? Also got to be 60. How many volts? 60. Do I know resistance? Do I know voltage? Then I know current here. How can I find, oh, current is V over R. What's the current in amps in this circuit? Sorry? 6 amps? What's the current in amps in this circuit? 4 amps? What's the current in amps in this circuit? 3 amps? When these join together, how many amps will they form when they join together? Does that confirm my answer? Aha! I found it 2 different ways. I know I'm right. So, I total is 13, R total is 4.61. They wanted me to find V and I for all resistors. Have I done what they wanted me to do? Yes. Hey, which of these 3 light bulbs is the brightest? Find the power of each of these. V times I is probably easiest. V times I. V times I. Which bulb is brighter here? The smaller resistor, which is a little bit counterintuitive for some people. I don't usually... I find parallel circuits, my initial guesses are often wrong. Jacob, you want to give him an elbow? You know what? As we call it now, give them a meta world peace. And is the document actually going to say that world peace has been suspended? Which is a little ironic when they... Anyways. I'm sure somewhere there's a lawyer chuckling as he types up that one. Suspend world peace. Example 8. Those of you that aren't basketball fans, zing over your heads. But this is an example of the kind of circuit I'm going to expect you to analyze, expect you to handle. The question says, what can be said about the voltage drops across the resistors in the circuit below? I'm going to see if we can't analyze as much of this as we can. Let's see. I'm going to try and redraw this so that here's my battery still. Write this down. I want to replace these two parallel with one single resistor. How would I replace this with one single resistor? 1 over 10 plus 1 over 15 reciprocal. Those two are the same as one 6 ohm resistor. I want to replace these two with one single resistor. Can you find out what this equivalent resistor is to those two? Because these two are in parallel. Can you go 1 over 20 plus 1 over 5 and then reciprocal of that? And you need to practice this, which is why I'm encouraging you to do this on your calculator, not mention any names. What'd you get, Connor? 4? And I'd like to replace these two with a single resistor. What are two 12 ohm resistors in parallel the same as one single resistor? What's 1 over 12 plus 1 over 12? Is that 6? Also, yes? And then don't forget to take a reciprocal when you're done, right? Now, why is this quick sketch so nice? Mitchell, are these all in series? Oh, you know what? I can tell you the total resistance in this circuit then. 16. This whole mess here is the same as, mathematically, one 16 ohm resistor. Oh. Do I know total current in this circuit? Do I, Nicole? Did they tell me the current leaving the chairlift? Look at the diagram, please. Yes? What? How big? Oh. Well, you know what, Nicole? I'm going to say that total voltage equals total current times total resistance. I now know the chairlift. They didn't need to tell me the battery. I can figure out what it has to be. It's going to be total 5 amps, total 16 ohms. How big is this battery? Kara. Let's go label that. Oh, and you know what? Let's even put it here in my little sketch. Now, eventually, Brandon, you'll probably get good enough where you don't need to completely resketch, but this is a good little trick. Or sometimes what I'll do is I'll just go like this in pencil, and that'll be my replacement for that. I'll go like this in pencil, and that'll be my replacement for that. I'll go like this in pencil, and that'll be my replacement for that. If I don't feel like rewriting everything. Oh. What's the current running through this mathematically equivalent 6 ohm resistor? Zay. No, no calculator. What's the current leaving right here? 5 amps. What's the current going right here then? 5 amps. How high must this hill be then? What's the voltage drop? Sorry? So are you telling me that from here to here has to be 30 volts? So you're saying that this right here is 30 volts and this right here is 30 volts? That's correct. Do I know 2? Then I know 3. Find the current in the top resistor. By the way, if you haven't written down V equals I times R somewhere on your page, I would. How do I find current, Mitchell? 30 divided by... Oh! The current in the top resistor is 3 amps. What was the total current, Mitchell? I'm pretty sure the bottom one is 2 amps. Double check. Can you also get that by going V divided by R and solving it in a different method, and now independently we have a check of Kerkhoff's loss? Yeah. Oh, Mitchell, we said that these 2 resistors were like one single 4 ohm resistor. What's the current mathematically flowing through this 4 ohm resistor? Yeah. Oh, you did say 5? What's the voltage that we lose going through this hill then? So you're telling me that from here to here, 20 volts? So that means this guy must be 20 volts, and this guy must be 20 volts. You're correct. Oh, do I know 2? Then I know 3. How many amps are going through this resistor here? Jacob. That would suggest that 4 amps is going through there. Double check by doing the arithmetic. Do you get 4 amps? Yes? Oh, so we found it 2 different ways. We're pretty sure we're right. How high? Oh, how high was the hill, Connor? What did I lose here? What did I lose here? What must I lose here? Now, I could also double check, because is the current in here also 5 amps? And can I go I times... Ooh, I can get that 30 volts in 2 different ways, going I times R and using Kerkhoff's loss. So are you telling me, Connor, that this is 30 volts and this is 30 volts? Yes? Oh, how many amps here? How many amps here? Now, there's 3 ways to do this. First of all, are these 2 resistors identical? What do you think happens to the current then? Splits in half. It's going to be 2.5 and 2.5, I bet. If you go V divided by I, do you also get 2.5 and 2? Oh. There, we've analyzed this circuit. Okay, which is the brightest bulb in that circuit? Really quickly on your calculator, go V times I for each little individual circuit. Let's see. Or you can do it in your head. 90. I'll even add it to the diagram. 90 watts. 60 watts. 20 watts. 80 watts. 30 times 2.5 is 60 and 15... 75 watts? Oh, top bulb's the brightest. Is that okay, Katie? Yep. By the way, you notice I gave you the resistances. Again, if you know 2 things, you know 4 things. I could have mixed and matched, and in one of these, instead of giving you its resistance, maybe I could have given you its voltage or its current, or that usually makes it way easier. The toughest questions are where you have no current anywhere on the diagram. Then you have to rewrite it as a mathematically equivalent 1 resistor, 1 current, or 1 voltage, and go from there. Example 8 illustrates an important point, a shortcut, if you will. The voltage drop across parallel resistors is the same as the drop across the equivalent resistor in the equivalent circuit. In other words, I'll come back to that, but hey, if I lose 30 volts, I must lose 30 volts in each of those. If I lose 20 volts, I must lose 20 volts in each of those. If I lose 30 volts, I must lose 30 volts in each of those. So here's how the wiring works in your house. Okay? In a household circuit, plugs and lights are wired in parallel to 120 volts AC. Each circuit has a circuit breaker in the circuit. The circuit breaker is an automatic switch that opens when the current exceeds a set value. Most of your circuit breakers are 15 amps. More than that, fire bad. When the switch is opened, ka-choom, no more current can flow through the circuit because there's no ski hill that will take the skiers back to the bottom of the chairlift. Example 9. If we connect a 120 watt hairdryer and a 500 watt TV to the same power outlet, the same circuit, will we cause the 15 amp breaker to trip? This is how, if you've ever blown a breaker in your house, this is what was occurring. This is why when you unplug one of those devices, oh, now the circuit will go. So let's see. Brandon, what's the total voltage leaving the chairlift? Now this is AC, but treat it like a battery. What's my total voltage? How many volts must be coming out of this plug here? If I can get back to the bottom of the chairlift following that path, gotta be 120 volts. And how many are coming out of this plug here? This is why each plug that you plug into gives you 120 volts. That's how it works. Your houses are wired in parallel. Okay. Oh, how many watts are in this hairdryer? 1200 watts. How many watts? 500 watts. Oh, if I know 2, I know 4. So we have this. V equals I times R, and power equals VI. I'd like to know if we crack 15 amps. I know power and voltage. Kayla, how would I get the I by itself here? Here, get the I. Yes. So how many amps are flowing through this section of the circuit? Well, it's going to be 1200 watts divided by 120 volts. In this plug, we have 10 amps flowing. Here, I have a 500 watt TV and 120 volts. How many amps is this plug drawing? Kara, what did you get? I have no idea what you said. 4.17, is that right? I'll even go 4.2 to keep the math simple. So Kara, we got 10 amps there, we got 4.2 amps there. What's the total current in this circuit? Let's see. Now, I can't draw arrows because AC goes back and forth, back and forth, back and forth, back and forth, back and forth. But if they both go this way, how many meet right? How many amps get together right here? Are you saying 14.2? Because if you are, you're right, but I can't hear a word you're saying. Okay, total current 14.2 amps. Are we going to blow the breaker? Just barely not. Oh, if we plug one more thing in, Mitsu, will we blow the breaker? Yep. Yep. How many of you have ever blown a breaker at your house? Okay, there it is. And it starts what? When you plug that one appliance in, flick, boom, it goes right away. You've just made the current jump more than it should. Or if you have an appliance that has a varying rate of power, so maybe you have a microwave that goes off and on, maybe it made it through the first round, but when it kicked the power up a notch, boom, then it went out. Next page. Homework. Okay. Number 1. 2. 3, these are all in series. Series is nice, easy math. Number 4 asks, which resistors are in series? Those two and those two. Everything else has junctions between them. But there, you can think about it. Skip 5. 6 is good. 7 is good. 8 is good. Yeah, 9 is good. Skip 10. $11. Skip 12. $13 and $14. Sounds like a lot, but you got a full half hour, and I wasn't kidding. If you get last lesson and today, realistically, you got a good shot at getting 100% on the test. Everything I'm going to be doing for the next few days, again, Nicole, should hopefully be obvious. Like, oh yeah, I would have thought of that. The only weird part is when we start recharging batteries and then I allow you to go backwards up the chairlift. That's where my ski hill analogy breaks down. But when you're recharging batteries, what you're really doing is you're forcing electrons to go in the opposite direction than they want to go. Okay. Right click.